this is going to be in saturation, and if I call the operating point drain voltage as some VD, and if the operating point drain current is ID, so what is the operating point drain voltage in terms of ID? Can you tell me what is VD? VDD minus? So I have this potential is VDD. The DC current flowing here is also ID. Remember, DC current flowing through the capacitor is how much? So this is 0 DC. So which means this is also ID. So the DC potential at drain is this. And in saturation, you know the current equation. Let me just write it once. Half mu n COX W by L, VGS minus VTH square. Okay. Now it turns out in practice, this VTH has a lot of variation. Even mu n COX has variation, but this is negligible. But VTH has a lot of variation. That is, let us say you might have assumed that the threshold of your transistor is 0.5 volt undesigned, but once the chip is fabricated and you get back, you might notice that VTH changes a lot. Right? Or even other thing, VTH changes with temperature also. Right? So which means if VTH changes with temperature, what can you say about the drain current? That will also change because we are keeping VGS to be fixed. Correct? So this will go and change my drain current. If my drain current changes, what can you say about the operating point drain voltage? That will also change. Right? So all the operating points will sort of get drifted apart. Right? And not just that, even if I look at the small signal GM, remember GM is square root of 2 ID mu n COX W by L. With temperature, let us say the threshold voltage changes, current changes. So which means even the GM is going to change. Correct? So which means this is a good news or a bad news? Bad news, right? Of course, you can't say that my circuit will work properly in Kanpur in the month of January, when the temperature is close to 0 degrees Celsius. When it comes to scorching heat in July, it will not work. That is not something you can sell. So we have to do something about this. Right? And tell me here in this equation, staring at this, if I have to make sure the operating point drain voltage doesn't change, what should I be keeping constant? If this has to remain constant, what should remain constant here? ID. If I somehow make ID to be constant, my operating point drain current of course is constant, this is constant, and even GM is going to be constant. Fine. And that's why we prefer this kind of biasing, where we try to fix the current to be constant, and that's what we call constant current biasing. Where my goal is to make sure that my drain current is equal to some current, say some reference current of, I don't know, some value 100 microamps or something. Let's see how we can accomplish that. So again, let me draw the transistor. This is my transistor. My job is to make sure that the current flowing in the transistor is constant. Now remember, transistor does not generate current on its own. We should feed in something so that it provides current. And what is that something? Gate to source voltage and drain to source voltage also. And of course in saturation, it's only VGS, right? So which means, let's say this is connected to something. Let's say it's connected to VDD itself. The current mainly depends on VGS. So I should be actually providing some VGS here so that it provides a current. But if I keep the VGS to be constant, if the threshold voltage changes, current will also change. Which means if I have to retweak my current, what should I be changing? I have to somehow change the VGS so that the current is constant. Is that clear? So somehow I have to keep it programmable. Okay. Now tell me, let's say this is a lab experiment, lab setup. I've given you all sort of ways to change the voltage, measure current, everything. What would be your way of approaching this problem? I want to make sure my drain current is equal to some reference current. I give you this reference current also, right? So how would you try to do this now? I mean, let's say I give a current source of 100 microamps, right? I mean, what is my goal? What am I trying to do now? Yeah, I have to somehow keep ID to be constant. So what should I be doing? I should compare ID with reference current, and then what do? That's what you should do. Is that clear? First I'll measure ID somehow, compare it with the given reference current of 100 microamps, and based on that I'll go and change my VGS so that the current is constant. That's the only thing, right? So let me write it here. So first thing is I'll compare ID with IREF, correct? So this is in English. So if I were to write it mathematically, comparison is essentially doing what mathematical operation? I'm basically subtracting two quantities. So let us say I want to somehow get IREF minus ID, correct? And let's say for example this is greater than 0, which means my drain current is smaller than required, or it is larger than that required value? Smaller. So now as a corrective action, I should increase my ID or decrease my ID? I should increase my ID. So I'll say need to increase ID. And how will you increase ID? I have to increase what voltage? So which means I'll have to go and increase VGS. Right? It's the opposite case, this things become opposite. So which means if you are in a lab setup, essentially you will be here, you will be checking the drain current and then going and tweaking. Right? You see this current and go and change the voltage so that the current is constant. Right? Now, of course, this is not practical because you can't say I'll ship one human being with every transistor and he will stay with the customer all the time and making sure the current is constant. Obviously not practical for a lot of reasons. So this is somehow, so we should make sure that we accomplish this automatically using circuits. We can't rely on human beings. So of course now we have the algorithm in English. You just have to translate it to circuits. So let's see how to do that. Let me erase this. So let's say this is my gate voltage VG. I have, let us say, a reference current of 100 microamps. So what is the first step I have to do here? I have to compare the two, which means mathematically I should be generating this current. So let us say I have two current sources. I have to subtract the two current sources. What is the simplest way I can subtract? Or I will ask the other way. If I want to add two currents, what do? You put them in series or parallel? Correct? Or in other words, you will do this. The current is getting, sorry, I'll do this way. Current gets added. If I have to subtract the current, what do I do now? Yeah, I'll just change the polarity of, let us say, this fellow. So which means if this is IREF and this is ID, the current flowing out of this node is IREF minus ID. So remember, adding or subtracting currents is the most trivial job you can do in a circuit. Okay. So I already have ID, and let us say I give you a reference current IREF. So just have to connect it like this. Okay. So the current flowing out of this node is your required current. So first job is done. Now is the second job. I have to see. Okay, let me erase this actually. This is clear. Now is when we have to go and change VGS accordingly, right? And remember that in practice, at all of the nodes, you will have some parasitic capacitance to grow. So which means this excess current of IREF minus ID is effectively getting pumped into the parasitic capacitor. And let's take this example where the difference current is greater than 0. So effectively have a positive current that is getting pushed into this capacitor, right? So if you have a constant positive current getting pushed into a capacitor, what will happen to the voltage? That will keep increasing. So if I call this, let us say Vx, maybe I'll do a different color. Let's say this is Vx. So in this case, my Vx will increase. Fine. Now I know that as a corrective action to increase ID, I need to increase Vgs. So which means I should go and increase my Vg. Correct. Now I see that in this case my Vx is already increasing, and I actually have to increase Vg. What is the simplest thing to do? I'll basically go and short, right? Because I want to increase this voltage, but I see this voltage is already increasing. So why bother? I'll directly go and short. Well, you want to have a pizza, you don't have, your friend has a pizza, what do? You take it from him. That's all. Is this clear? So I'll erase all the parasitics, or maybe let it be there. Is this clear what we are doing? So now if you think about what we have done, we are essentially sensing some quantity, and based on that information we are feeding this information back and changing something else to keep a quantity constant. So what kind of general principle we are using here? We are using some kind of feedback, and this is basically negative feedback. So now if you think from the first class, we wanted to make an op amp or something with an infinitely large gain. Why did we want to make something with an infinitely large gain? Yeah, but where will I use such infinite gain systems? Negative feedback. So I started with the goal of making an op amp to be used in negative feedback, and seems like to make an amplifier and to bias it properly, I again rely on negative feedback, right? So that's the beauty of this. That is nature leading its way to achieve your goal. And some jargons. This typically we call it as diode-connected transistor. So maybe sometimes I'll use this term, diode-connected. Again, this has historical reasons. It turned out, for 40 years back when the transistors was bipolar junction transistors, the moment you made this connection, that effectively became a diode. So people called it diode-connected. But with MOSFET, that's no longer the case, but the name just stuck around. Great. And yeah, and now let us say I give you the reference current. I know the reference current is 100 microamps, or let us say something. I give you the threshold voltage and mu and C OX. Can you find the gate voltage now? Will you be able to find the gate voltage? Yes or no? How will you find it? You know the current equation. It's half mu and C OX. But once again, remember that this equation is valid in which region? And for saturation region, what is the condition on VDS? So here is it getting satisfied? What is my VGS and VDS? How are they related? They are equal. VDS is equal to VGS minus VTH. So both are equal. My threshold voltage is obviously greater than 0. So we are okay. So this transistor is operating in. Is that clear to everyone? Okay. So now we know the current equation. We can basically find what is the VGS. VGS will be the threshold plus square root of 2 ID by mu and C OX. I'm just rewriting this equation. Okay. Now ideally remember that if you were to not do this and use an external voltage source to keep the current to be Iref, you will need to exactly know what is my mu and C OX, VTH, etc. Only then you can accomplish this. But this act of doing this negative feedback connection automatically makes sure that the gate to source voltage is set to this value so that the current is equal to Iref. Is this clear? Now you don't have to do all the hard work. The negative feedback will automatically ensure that the drain current here is equal to the reference current, and that is getting accomplished by setting an appropriate gate to source voltage. So which means now, let us say, due to temperature, the threshold voltage of this transistor changes. What will change in the circuit to keep the current constant? Vg will change appropriately so that the current is remaining constant. For example, let us say threshold increases by 100 millivolts. How much will the gate voltage increase by? Should also increase by 100 millivolts. Because remember, current depends on Vgs minus Vth. This quantity must be constant. Is it okay? And typically we'll write it, let's say call this transistor M1. Maybe I'll take it to a different page. Let's see. Where is this? So just a notation that we will be using usually. So let us say this current is Iref. To denote this voltage, which is VGS, we will say it is VGS of the transistor M1. This is biased at a current of Iref. Basically, instead of writing this whole expression, that is Vth plus square root of 2Id by mu n CoX W by L, you will basically be using this shorthand notation. I'll say it is VGS of transistor M1 when it is biased at a current of Iref. So which means once I know the threshold voltage and mobility, I can find VGS. Just a notation that we'll be following. Okay. So okay. Great. So now let me take this. So now we know we can do this thing. This negative feedback connection will ensure that my, let's say this is some I0, the current flowing here is going to be I0, and my gate voltage will automatically get set. Right? So the nice thing is, now if I want to make sure another current is biased with the same current, what can I do? Sorry, another transistor, I want to make sure that current is also same. What can I do? I basically give it the same gate voltage. Of course, in this we are assuming that these two transistors are identical. That is, that they have the same mu and CoX, same width, same length, same threshold. So, and that is something that's a reasonable assumption to make on chip. So, which means if the threshold voltage of this transistor changes, the assumption is even the threshold voltage of this transistor will change by the same amount. Once again, on chip, when things are all close by, this is a reasonable assumption to make to a first order. And of course, you guys know, if you already didn't know, this typically we call it as current mirror, because we are sort of mirroring, this current here. Oops. We are copying this current and mirroring it to this branch. So which means I can copy this to another identical transistor. That current will also be I0. Now if I want to get 2 times I0, what is the simplest thing I can do here? I mean, or let us say I have 2 transistors, each carrying a current I0. I want to get 2 times I0. I can connect them in parallel. Correct? This will be 2. Okay. Is clear? I can remember this negative feedback connection is making sure that this gate voltage is set to a value that ensures that the drain current is equal to I0. So any transistor or any identical transistor that is fed by the same gate voltage will also carry the same current I0. That's all. So it turns out, having 2 transistors in parallel is equivalent to doubling the width of the transistor. That is, the width becomes 2 times W. That is, what I am saying is, instead of having 2 transistors in parallel, in principle you can have a single transistor whose width is 2 times W. So in general, if you want to scale currents, you basically scale the widths So scale widths for scaling currents, because as you see, this is something fundamental, right? This is as though you're putting multiple things in parallel. So scaling width will almost guarantee that the current is scaled. But that's not the true with length. Okay, sometimes people think that, so that is not fundamental, right? So don't scale length. We'll see in detail later, but anyways, just have it in. Okay, great. So now we have slightly digressed, because our goal is to make sure that I bias my common source amplifier, correct? I have to bias this fellow, that's my goal, and I want to make sure this guy is biased with a constant drain current. Okay, is that clear? And I know how to generate a gate voltage that ensures that the drain current is constant. That is this mechanism. So let's try to form the full circuit. So first let me draw our main common source amplifier. So this is the transistor. Now let me draw the load side, because that is easy. I have a load, and how will I connect the load to the drain? I'll put a capacitance of sufficiently large value, and of course here I'll have another resistor for providing the drain voltage. So this much is the same as before, nothing has changed. The only thing that we are going to change is the gate voltage. Okay. And remember that let's say this is my small signal voltage and the inherent source resistance Rs. Let me draw it again neatly. And I also know how to generate the required bias voltage so that the current through the transistor is constant, and that is essentially this. Maybe I'll make some space and draw. If I keep this to be some reference current, the gate voltage will get set to a value so that the drain current is IRF. So now I have the small signal voltage, the DC voltage. How will I connect the two? Okay, remember that. I mean, let's start with scratch if it's again not comfortable. So can I connect it directly? No. So I have to shift this voltage by the required gate voltage, correct? If I somehow measure this voltage and put a voltage source of that value, we are set. Now of course we can't have a floating battery. What do you replace it with? Great. So let me replace it with a capacitor. And remember, this capacitor has to be charged to this voltage. So what do you do now? Should I connect it directly, or what do I do? Again, have to have a resistance. I'll call this RB. So this way the capacitor is charged to that required voltage, so that DC shifting is done. So you can remember, anytime I give you a AC signal and a DC signal, this is how you kind of bias it. Think of it this way: I can't connect the AC signal directly, the small signal directly. You have to shift it by a DC voltage. So in principle, you try to put a DC voltage source, but then you replace the DC voltage source by a sufficiently large capacitor, and make sure that the capacitor is charged to that required DC voltage. So this way you don't have to remember anything. Understand what we are doing. That's all. Yeah.
What's wrong if we keep a DC voltage source?
Oh, you are asking why don't we have this? Turns out in practice it is not available. I mean, you are connecting your you would have done all lab experiments, right? All signal sources, you would have seen that has a common ground, and it has to be connected to the electrical ground of it, so that grounding is set. So which means in general all voltage sources typically have like this, unless you have that Duracell battery. That's there you can access both terminals, but otherwise it is always connected to grid. And that said, I mean, even if that were possible, you can't put a voltage source inside a chip, correct? That's the even more fundamental problem, right? Because this finally I want to make sure this part of the circuit is fabricated on a chip. I can't have a voltage source inside a chip. Great. So now let's actually quickly make sure that for small signal things are working fine. So, but before that, this connection is okay. Yeah.
Can we ignore RB because RB is connected to gate of both transistors? No current is going to flow.
Okay, good question. So what we'll do, we'll look at the small signal now, right? Then we'll understand what happens. Just have it at the back of your mind. We'll address it immediately. Okay. So let's try to draw the small signal. So again, for small signal, capacitors are, I mean, these capacitors, how will they behave? Short. So we'll make it all blue. And the DC source is also grounded. So this is also ground. And these two fellows appear in parallel. So I'll simplify the circuit like this. Is it okay? What I have done till now, is it okay? Great. And yeah, now let's look at this fellow. So again, I have a DC current source. For small signals, what do you do for this? Open. Current becomes 0. Again, this, when I say small signal, I am looking at changes in the quantities. This is a constant current, 0 change. So it's 0 current, sorry, which means the current source is open. Now let's look at this voltage. Let's say this is VG. Again, for simplicity, let's ignore R0 for all the transistors. That is, GDS or the Y22 is assumed to be 0. Let's start with that assumption for starters. So first tell me, let me label the transistors also for simplicity. So let's say this is M1 and this is M2. Okay, so I'll call this VG of 2. Similarly, I'll call this to be VG of transistor M. Now let's try to draw the small signal. So for small signals, how will this transistor behave? Voltage control. Any transistor for small signals, voltage controlled current source. So what will be the current drawn by the transistor? What will be this current? Gm of transistor M1, Gm1 times VG1 or VG2? 1. Okay. Is this fine? Any confusions? So here it looks like this node voltage is VG1, and from this node I am drawing a current that is proportional to VG1. So how can you model this as resistor? What is the value of the resistance? For small signals, the moment you have this connection, you can model it as an equivalent resistance. Right? Now again, question to you, based on whatever you already knew about nonlinear circuits and small signal, nonlinear things, does it make sense that this behaves like a resistor for small signals? Why? Exactly, 2-port, not 2-port. Yeah, remember that a MOSFET, how many terminals it has? 3 terminals. But here I am basically shorting gate and drain. So how many terminals I have? So how many port network is this? 1-port network. We already saw any nonlinear 1-port network for small signals is a same thing. Should not be surprising at all that this happens. And again, similarly in the future, anytime you have a case like this where I have a 3-terminal element where some terminals are getting shorted, so that effectively we end up with a 1-port network, you can replace it for small signals by an equivalent resistance. So now this is clear, so let me just replace it with a resistor. So what I am going to do, I am going to replace this fellow with a resistor of value 1 by GM1. Okay, so I'm just going to make it. Okay, this is okay. Now what is VG2 now? Small signal VG2 in terms of Vin. RB plus 1 by GM1 by RS plus RB plus 2. Okay. And ideally, how do you want this to be approximately equal to Vin? Right. So now coming back to his question, if let us say I didn't have RB, right? So this goes off. You'll have a case where it's 1 by GM1 plus by RS plus 1 by GM1. It turns out in practice you won't have a large gain. So typically you'll have large GM and large R naught, correct? So your GM is going to be really large. So what can you say about 1 by GM? Small. So which means if I have just 1 by, if I don't have RB, can I make this fraction, how do you think this fraction will be? Yeah, I mean like very, very small. That's not what you want. Does that answer your question? So that's why we are adding a series resistor RB. Cool. So this is done. No question? Why 1 by RS? I mean it's a voltage division, right? I have two resistors in series. Okay.
Let us say we don't have RB.
Okay.
And 1 by GM is sufficiently small.
Then it's okay. I mean, let us say, see, the idea is you want to make sure this fraction is as close to 1 as possible. The idea is to make sure this fraction is as close to 1 as possible, right? Without RB, if you can make sure that GM is really small and it's much greater than RS, then you're okay. But in practice, typically you want to have a large gain. So GM will be large, R naught will also be large. And remember, these two transistors should be identical. So if the amplifier has a large GM, even this fellow will have a large GM. Okay, so that's why that's a problem. Is it okay? So then we can finish. What is the small signal current now? ID. GM 2 times. Yeah, V in, VG2. VG2 is V in. So what is small signal V out? Can you finish it completely? Minus GM2 RL parallel RD times. So it's working as expected. Our biasing didn't screw up anything else. Okay. Any questions? Is it clear? So now, right, remember the bottom line of whatever we have discussed so far is when we are biasing, we want to make sure that the bias current is constant. So we want to have some kind of constant current bias and not a constant voltage bias. That's all. And we ensure that the current is biased at, we are biasing at a constant current by doing some kind of feedback. You measure the current and make sure that the gate to source voltage is adjusted. Now, interestingly, the drain current in the transistor flows between which and which terminal? Drain and source, right? If I had to change this current, what voltages should I be changing? VGS. So I can change the gate voltage, source voltage. Remember, the mechanism I use is I sense the drain current and then change my VGS. Now you see my drain current, I can sense it either from the drain side or from the source side. So I can essentially sense either at the drain side or at the source side. Similarly, for changing VGS, I can either change the gate voltage or the source voltage. Is this clear? And when I did this connection, Where were we sensing the drain current, from the drain side or the source side? We were sensing it from the drain side to sense the drain current. And which voltage did we change? Gate voltage. So basically we did this combination. But how many different combinations you can have? 4 different combinations you can have. So 4 different constant current bias schemes can be obtained actually. So we will look at only one more, that is this interesting combo of sensing the current at the source side and changing the source voltage itself, because these two are pretty commonly used. So we'll just look at these two, and this is much simpler. We'll finish in a couple of minutes. But is the overall principle clear? The point is we want to do constant current biasing, and that can be established by some kind of feedback mechanism, which means you sense the drain current and go and change the gate to source voltage. Now I can sense my drain current either at the drain side or at the source side. For changing VGS, I can either change the gate voltage or the source voltage. So this gives me 4 different combinations, that's all. So we'll just look at this combo where I am sensing at the source side and I am changing my source voltage. So again I'll have the transistor. So if I'm changing the source voltage, my gate voltage should be constant or it should be changing? Gate should be kept constant. I'm changing only the source voltage. So let's say I hook it up to a constant gate voltage. So once again, remember I'm trying to sense the current at the source, and I have to compare my drain current with the reference current, and this should be happening at the drain side or the source side? Source side. Now this is my drain current. Let us say I have the reference current. How will I subtract these two currents now? I can basically do this. So this is going to be, is that clear? I am sensing the current at the source side and comparing it with IREF at the source. Clear? Now again, as usual, we have parasitic capacitors. Let's take an example. Say ID minus IREF is greater than 0. If this is the case, as a corrective action, what should I do to ID? Increase it or reduce it? I have to reduce ID. If I have to reduce ID, should I be increasing the source voltage or reducing the source voltage? Increase the source voltage. Fine. So now again we can look at this, right? So look at this node. I am taking this case, ID minus IREF greater than 0. I have an effective positive current getting pumped into the capacitor. So this voltage will increase or decrease? That is going to increase, and that's exactly what you want also. Yeah, you don't have to do anything else. This is enough. Is this clear? Not clear? Now, do you understand till this point that we are taking the difference between the currents at the source? And if, let us say, this current is greater than 0, the difference current is going to flow to the parasitic capacitor. A positive current flows through a capacitor, so the voltage will start to increase. Is that clear? If this voltage increases, the source voltage of the transistor increases. If the source voltage increases, maybe I'll write it, source voltage increases. So what can you say about VGS? Decreases. Then what happens to the drain current? And that's exactly what you want. Now you don't have to do anything, you just hook this up to a constant voltage and put the required reference current here. The source voltage now will adjust automatically to make sure that you have a required VGS for sustaining a current of IREF. Is okay? Again, remember what is the cause and what is the effect, right? In the transistor, the cause is gate to source voltage. The effect is drain to source current. Okay, so if you want to fix something at the effect, that is if you want to fix the drain current, should be going and addressing the cause, that is either the gate or source. So which means, I mean, because this is again sometimes people get confused, so which means if I directly put in a current source and put it to the drain, the gate voltage will not get set automatically, right? Because here you are sensing the current difference. Iref minus ID is sensed, but that sensed information is not getting fed back anywhere. This should either be fed back to the gate or to the source. So here the feedback is happening at the source, so the gate to source voltage is getting adjusted. Okay. So which means if this voltage is Vg, my source voltage will be set to Vg minus the VGS of this transistor in biased at a current of If. That's all. Because I am calling this to be the VGS. Remember, I need to have a particular VGS so that the current is constant. So the source voltage will be whatever you connect here. Maybe I'll call it VB. This will be VB minus the VGS of the transistor when it is biased at a current Iref. Okay. Any questions? So now I'll give it as an exercise for you to actually build a common source amplifier with this. So remember, for biasing, this is what we are doing. Okay, and this should be connected to some. For small signals, I should have something like this. So I'll give it as an exercise. You guys try to work out and find out how will the total circuit look like. Right? So we'll look at it briefly in the next class and continue from there. Okay. But please take it as an exercise. Do it yourself. Only if you try it yourself and draw, you will be able to understand and follow. Right? And again, like I told, don't try to memorize anything. That's not going to help in circuits. Okay. So I'll stop here. We'll continue.